Hi everyone, and welcome to this open day from School of Ocean Sciences. I'm Mattius Green, I'm a physical oceanographer and I'm the school's senior admissions tutor. And over the next 15 minutes or so, I will talk a bit about the school, give an example of what I think is some exciting research that ties into what you will be taught in some of our modules, and we will look at some careers that our postgraduates have taken in their life. We've been at the shores of the Manor Bridge for over 50 years. The school buildings are over on the right here, and this blue vessel is our ocean-going research vessel, the Prince Maddock. And we're unique in the UK that we cover all aspects of ocean science under one roof in a dedicated ocean science department. We take about 200 students a year across all our degree courses, and this presentation is directed towards the oceanography side, so the courses down on the left here. And they can all be traditional 3-year BScs, or you can extend them into 4 years and get an MSci and integrated masters by doing a research project in 4th year. All the courses can have a placement year added to them, and that includes opportunity to study abroad or do internships for charities, for government agencies, or industry. And we've had students go all around the world on their placements for those who wish to do those. And if you don't fulfill our entry criteria, don't despair. You can do foundation year, which if you pass it, when you pass it, you go straight into our first year on your chosen course. And we're in a truly unique location in the UK. You can be up in the mountains in the morning and look at glacially sculpted 300, 400 million year rocks. And in the afternoon, you're down on sandy beaches or rocky shores and look at very different processes at play. We have state-of-the-art facilities, lab facilities and lecture rooms. We have a great selection of equipment. We have access to supercomputing facilities, workboats, and of course the Prince Maddock, which you will go out on and get experience of working at sea. And we use the environment as our laboratory. We teach you in traditional lectures and tutorials and in the lab, and then we get you out into the environment, out on our doorstep, to look at the environments and the processes and the products you have been taught about in class. We're in top 2 in the UK for ocean science research as evaluated by the government, and our research truly stretches from pole to pole. We have scientists working with ice in Antarctica, Southern Ocean, up through tropical coral reefs and into the Arctic. And from below the seafloor, up through the seafloor, the water column, to the surface and into the atmosphere, looking at climate. You will be taught by world-leading researchers. We bring our research into the classroom so you know that what you're being taught is at the forefront of the subject in the classes you're sitting. And I'm going to talk a bit about my research now, and I work with tides and how tides have changed on long periods of time and how that is important for other parts of the Earth system, that is, for the planet as it all comes together and holds together. Did you know that the size of the moon in the sky is set by the history of how the continents have been organized on Earth? Well, that is true because as the continents move around due to tectonics, they change the size and shape of the ocean basins. And the tides, the energetics or size of the tides depends on the size of the ocean basins. So as the continents move, the ocean basins change and the tides change. The tides have a spurious effect that they slow down the spin of Earth, so days are getting longer with a few seconds per million years. But because the whole Earth-Moon system is slowing down, the days are getting longer, the system must become bigger. So the moon is moving away from Earth because of the tides. And of course, the size of the moon in the sky is set by how far away it is from us, and that is set by the rate it is moving away from. And that rate is currently very large, it's about 3.5 centimeters per year. So day length is largely controlled by having a moon and having tides in the oceans, as we shall conduct. And tides are important for a whole range of processes. They drive currents, they transport sediment, but they also pump an enormous amount of energy into the ocean, the equivalent of 4 million Mars bars every second. And you can see here how the tide in October last year moves around Earth. And all that energy is really important because it stirs and mixes the ocean. And you can think of it, if you have a cup of coffee and put sugar in, you get some sugar going at the bottom of the cup. And if you put a spoon in and stir it, that sugar is lifted up through the cup and evenly distributed. And in the ocean, the tides and the wind have the role of the spoon. They stir the ocean and mix things, heat, water masses, salt, pollutants, and nutrients from depths up to the surface. And that's a really key process. And we're going to jump into 3 different steps, time slices in Earth's history, and see what the tides were up to and why that matters. And the first one is the Eocene, 55 million years ago. Earth looks slightly different than it does today, with small Atlantic and quite large Pacific, and Australia is still stuck to Antarctica. And you can see that the tides weren't doing as much as in the previous slide. It's more blue in this than it was in the previous one. But it's an interesting period, this, because it was a greenhouse climate. This is where we'll end up in 200 years if we don't do anything and just keep burning all the fossil fuels we can find. Where it would be a lot warmer, no ice anywhere, and 80-meter higher sea level. And this figure here shows the sea surface temperature, average sea surface temperature as you go from Antarctica up into the Arctic, up to the North Pole. And this black line is present day surface temperatures, this temperature on the y-axis. It's cold at the poles and 27 degrees in the tropics over the equator. 55 million years ago, we have this orange line, where it's a bit warmer in the tropics, but you have tropical temperatures at the poles, and you actually have crocodiles and palm trees in the Arctic. And this flattened curve that isn't just lifting this black curve up can only be achieved in computer models of climate models, if you put more energy into the Pacific. That gives a stronger ocean circulation that can transport more heat from the equator to the poles. And our tidal results show that that energy was there. So the tides drive and flatten this curve 55 million years ago. And even though the tides in general were about half as energetic then as they are today. And if we jump further back, 400 million years ago, we're in a really important time in its history. Plants and insects have moved on to land, where vertebrates, that is things with spines, had yet to do that transition. So fish hadn't started walking on land yet. That happened about 396 million years ago. And you can see in the picture here, you see footprints that have been kept from a mudflat and found in a quarry in Poland for something that walked with just the same gait on land as a modern day lizard. The question is, why would you leave this environment? They had lungs, they could breathe, they had already been developed, they could breathe air, but why would you leave the comfy, warm environment in the ocean and go on to land? Well, we think that tides might have been one of many processes acting here. So you come in on the high tide and you get stuck when the tide go out if you don't swim back fast enough. And those who had large appendages, large fins, or something that looked like limbs, they could drag themselves back overland. And there was a buffet waiting for you once you were there. But you need to have large tides in the right location. And those early fossilized evidence come from South China over here, which you can see is yellow, which means we have large tides. And Poland and the UK was along the south coast of this continent here. And there were also large tides. So we think we've found one potential driver for why fish started walking on land. And this was Hannah Byrne's master's project that was out in a scientific journal in autumn. And Hannah is now doing a PhD in Sweden. Here she is holding a fossilized shoulder blade that has just been dug out of this clay quarry here. And if we go even further back to 635 million years ago, even further back up to 700 million years ago, Earth looked very, very different. All the continents were aggregated together in a supercontinent. And there's a supercontinent between now and then called Pangaea, around 200 to 300 million years ago, and this was called Rodinia, and sat there for a very long time. And this is an interesting period in Earth's history because it was a snowball state. That is, a huge ice sheet covering all land, and most of the ocean was frozen over. Probably only a belt around the equator that was ice-free. And as you can see, the tides were doing very little. And we think that that might actually have helped prolong the snowball state, because these glaciations, these ice ages, lasted tens of millions of years rather than tens of thousands of years like the ones that finished about 10,000 years ago. So that might have been prolonged by a weak tide. Of course, there was no life on land then. There was life in the ocean, and it survived and it evolved, and land will have looked, that wasn't ice covered, will have looked something like this, a very barren place. Now, this is actually a photo from the surface of Venus. And Venus is anything but habitable or able to host life today. It's 450 degrees on the surface and rains sulfuric acid. But 3 billion years ago, it had an ocean, and the tides in that ocean could actually have made Venus habitable by controlling its day length. It has a really strange, very, very long day, which was beneficial for it back then. So Venus may actually have been habitable, able to host life, a couple of billion years ago. At the same time, life started to take off on Earth because it had a tide that changed its day length. And this link between day length and climate and habitability is really important, we've started to realize. And the tides, of course, is a crucial controller of how long a day is. So what we have found, if we summarize this, I've talked about the 3 time slices in red, present day sits here at 0, is that the tides were weak when we had the supercontinents, Rodinia and Pangaea, and they will be weak in 250 million years when we hit the next supercontinent. And in between, they peak. And they're especially energetic at the moment. So we have something we call a supertidal cycle with weak tides during the supercontinents and strong tides in between. And this is really crucial, again, for orbital evolution and habitability, because it shows that continents are a key controller of rotation rate, which controls climate, which links habitability. So if you have continents, you might have a completely different ability to host life on a planet than if you don't have continents. So that's a piece of research that I think link all the different disciplines together: geography, geology, oceanography, climate science, and biology. And our graduates have gone into a very wide range of careers, and I've picked a few here. We have Emily and Bonita, who did geological oceanography. Emily works as a geotechnical engineer on the Thames Link in London. Bonita did a PhD and is now a senior geologist at Equinor in Norway, working on prospecting and geotechnical surveying. The gentleman with the enormous backpack is Craig Jones, who did marine biology and oceanography. He was the first Welshman to climb Everest. And he recently won a medal for his outstanding conservation work around South Georgia and Antarctica in the Southern Ocean. And he always travels light, obviously. Tilly Painter-Jones also did marine biology and oceanography, and she decided to go into industry and now works as manager of a fish farm in the Orkneys and is absolutely loving making sure that there is food produced for us in an environmentally friendly and sustainable way. Julia did physical oceanography, and she is at the National Oceanography Centre in Liverpool, working on predicting flooding from storms, from large winter storm events. And Jestin Woolway did ocean science, went on to PhD, and recently won a very prestigious and hard to get Research Council fellowship working on the impact of climate change on lakes. So this is an example of what our graduates are doing, and you will get a very wide transferable skill set in your degrees with us that will set you up for the career you want to, and the world is truly your oyster with a degree from ocean sciences in Bangor. That's all I have, and we will now answer your questions in the chat. Thank you very much for listening.